Okay, so in this problem, we're gonna try to apply what we did on the previous problem, on the previous video. So this is problem number 12, in which we have a piston cylinder device contains 5 kilograms of refrigerant 134A, which is basically the refrigerant used in the AC system of the cars, at 800 kilopascal and 70 degrees Celsius. The refrigerant is cooled at constant pressure until it converts to a liquid at 15 degrees Celsius. Determine the amount of heat loss and show the process on a TV diagram. Alright, so when I read this problem, there's a piston cylinder. So the first thing I do always is I do a piston cylinder assembly. Remember the procedure. Step 01, do a picture or a sketch. So why is this important? This will show you that this is a closed system. And now let's see, what do we know? We use refrigerant 134A as a substance. There is a constant mass of 5 kilograms. Initially at 800 kilopascals and an initial temperature of 70 degrees Celsius. Okay, just copying over here. So now this is going to cool down. And we go to a state that we know T2 is equal to 15 degrees Celsius, and the that is in the liquid state. Okay, so the question over here is to do the TV diagram. That's a must, and to find what is the amount of heat loss. So you see I have the problem statement. Now I can just remove it. So let's start by doing the TV diagram. T V, we do this special line over here, and what do we know is at constant pressure. So we know everything is going to go through a line of constant pressure over here, and let's say this one we know is constant, so P2 equals P1, so P1 equals P2 equals to 800 kilopascals. All right, and we know that this point here will be the saturated gas, this will be the saturated liquid. Okay, so the first thing to know is what we need to find out is what is the state at state 1. So at state 1, what do we know? P1 is 800 kilopascals and T1 equal to 70 degrees Celsius. So I have the tables over here for the refrigerant. So let's say I use table 812 over here, which is the saturated refrigerant. So for the table over here, so in order to know the state, I can try to find out what is over here the saturation temperature. Okay, so if the temperature that we have is higher than the T saturation, will be in this region. If it's lower, will be in this region. Okay, so we know it's 800 kilopascals. So we go to 800 kilopascal on table 812. Let's see if it's clear or not. We have that the T saturation is 31.31. So that means that 31.31 degrees Celsius. Okay, and what do we know from the problem statement? We know that T1 equals 70. So let's say we'll be somewhere over here. So T1 equals 70. So we know right away that our state will be on the superheated region over here. and this is 1. And we know this is 31.31. Our last temperature, let's say, will be over here. T2 equal to 15 degrees Celsius, and will be on the liquid state. So let's say this will be 0 and 2. And let's say it will be A and B. We don't really need A and B, but just for the figure. So you see the substance go from the gas, we become to the side to the gas, remains a mixture, and it becomes a liquid. So doing from 1 to 2, what is the amount of heat lost by the refrigerant? So in order to do that, we go to the basic equations that we have, which is what so far the first principle of thermodynamics. Okay, you know already under this form, even though the correct sign is Q plus, but your textbook uses this notation, will be equal to the total change in energy, where this is equal to the change in internal energy plus change in kinetic energy plus change in potential energy. In this problem, like in almost every single problem, we can neglect the potential and the kinetic energy, so that we have that the heat will be equal to the change in internal energy plus the work. Okay, so in this case, what is doing work? We know the pressure is constant, but the volume is going to go from V1 to V2. So we're going to have work done by the pressure. And we know that the work done by the pressure is equal to P dV. Alright, so okay, over here, if we rewrite this in function of specific volume, we'll have M, mass, specific internal energy, U2 minus U1, plus work done at constant pressure will be equal to P V2 minus V1. But you know that the specific volume equals volume of a mass. All right. So if I do just the basic algebra over here, we have that Q will be equal to M U2 minus U1. Now we substitute the V, the volume V by M, little specific volume times V, we'll have plus M P V2 minus V1. So this will be Q equal to M U2 minus 1 plus P V2 minus V1. Okay, so this is a good problem. I just realized this. So now we can just go and find U2, U1, V2, V1. We know mass, we know the volume. But actually, what is this expression over here? If you look into detail, this is really equal to Q, M, change in internal energy, plus M, P, dV. Or this is equal to M factor of du plus P dV. And what is this term? Do you recognize this term over here? What is work done by the internal, what is internal energy plus the work done by the pressure is enthalpy. So basically we have the other way to solve this problem that would be equal to m delta H, which will mean that Q will be equal to m H2 minus H1. So you see now that you have two ways to solve the problem. So obviously this one is going to be faster, this one will be a little bit longer. If you do it both ways, probably you might find a slight difference because those values from the tables are not really 100% exact. But let's just do it this way over here. Using the second equation, it's just going to be faster. All right, and then if you want, we can do that one over there. All right, so we need to find H1. So what do we know about H1? From the previous page, we know P1 equal to 800 kilopascals, T1 equal to 70 degrees Celsius, and we know the state is superheated, so we need to go to the superheated tables. So let me find the superheated tables. There we go. So they give us the values over here. So you see superheated refrigerant 134A, and they give us in megapascals. So 800 kilopascal will be 0.8 megapascals. So we go over here, go to 0.4 over here. You cannot see. I turn the page. Here we have 0.8. And we need to look at 70. So at 70 we have H1 equal to 306.90. So I write table A13. We have H1 equal to 306.90 kilojoules per kilogram. All right. Okay, so we need now to find H2. So what do we know about H2? Is on the liquid state. Okay, so you will think, okay, let me try to find the table here for the liquid state of the refrigerant 134A. But if you go to the textbook, you will find out that there is no tables. So if you remember the previous video, for incompressible substances, the property does not change much in function of the pressure. Okay? So we need to go to the saturated table and just look at the temperature and see what happens. So we go to the table A11. Okay, so table A11. And even though we know the pressure, we're just interested on the temperature. And the temperature is 15 degrees Celsius. So we are out of luck over here, but we are right in between. So if you look at this table over here, there is not really value for 15, but they give you 14 and 16, so you can just add those two terms and divide by 2 to find the enthalpy. So the enthalpy in this case should be equal to what? So the enthalpy, let me do a small figure over here. Okay, so we don't have the tables for over here, but we have the tables between this point and this point. So what we are trying to approximate here is whatever happens to the properties along this line, we're going to say it's almost equal to this. So this will be H fluid or V fluid, whatever we're trying to find. So what we need to do is to find at T equals 15 degrees Celsius, H2 will be equal to H fluid at 15 degrees Celsius. And that, oops, sorry, you could not see that figure. So let me go back and re-explain this. So I did that figure over here, and what I was trying to say is that, okay, you don't have tables for this region over here, okay? But on the previous video, we said that because the properties do not change much in function of the pressure for an incompressible substance, we can just look at this table here and look at the different temperatures. So what we do is we go to the tables between this point and this point, which is the saturated table, but we're just going to look at what happened over the saturated fluid. And we said the properties will be more or less equal, okay? So at 15 degrees, H of fluid, so this is the table, H will be, fluid will be this column over here, right? So let me mark here, if I can zoom down. All right, so we know the value at 14 will be 70.94, at 16 will be 73.72. If you go right in the middle, you add them together and divide by 2. So you will do, for example, H2 will be equal to 70.94 plus 73.72 divided by 2, and you get that H2 is equal to 72.33 kilojoules per kilogram. Again, sorry for forgetting zooming out. So I give you a little bit of time to copy it. Okay, so finally, we get Q, let's recall the equation, equal to M H2 minus H1. So this will give us, for the numerical application, Q will be equal to 5, 72.33 minus 306.90, which give us minus 1172.85 kilojoules. So is the negative sign correct or wrong? So let us remember that for the equation Q minus work equal to change in energy, for the first principle, if we use that sign convention, we have that amount of heat going in is positive, amount of heat going out is negative. So in this problem, basically what's happening to the system when we go from 1 to 2, this is losing heat. Okay, so if I need to put on this figure, the heat is going out of the system, which means negative. All right, and actually the work here is the opposite because of the sign convention. Okay, okay, so we solved the problem using this equation. Let us see what we get if we use this one over here. All right, just for a check. We're probably not going to get exactly the same thing, but we should not be that off. Generally, it's around 10% at the most. So let's say check. using equation Q equal M U2 minus U1 plus P V2 minus V1. And basically we just do exactly the same thing. So let's see. For U1 V1, what's the state we know is superheated. So before we went to table A13, probably we need to go to table A13 again. At P1 equal 800 kilopascals and T1 equals 70 degrees Celsius. So table A13, we need to look at 0.8 megapascals. So what do we have? 0.8, 70, so U will be equal to 281.83. And V1 will be equal to 0.03134. 0.03134. Okay, let me zoom out so you can look at it. This is basically what we have. Okay, so kind of do something similar now. For U2 V2, once again, we are in the liquid state. We don't have tables for the liquid state, so we go to the saturated liquid and we approximate at that point. We need to do that interpolation between 14 and 16, so we look at table A11 at the temperature 15 degrees Celsius. So let me zoom in. So at 14, 15 over here, we have the volume equal to let me see if I can move it up a little bit. Volume equal to 0.0008018 at 14.0008064 at 16, and we look at V fluid, okay? And then U fluid, which is this column over here, we have 70.56, 73.31. So if we add these two and divide by 2, and the same thing for these two, what we get is, so you get that U1 will be equal to, U2 will be equal to 71.935, and V2 will be equal to 0.0008041. Okay, so finally, if we go and substitute into the expression Q equal M U2 minus U1 plus P V2 minus V1, what do we get? Numerical application, we have 5 kilograms. That will factor out what? 71.935 minus, let's see, what was the value? 281.83 plus 800 kilopascal, leave it on kilopascals, times V2 0.008041 minus 0.03134. And this, once you plug all those numbers into your calculator, you get negative 1073.9 kilojoules. So you see that it's not identical to what we did before, but it's not that off either. So let's just try to see what is the error percentage. So that will be, so let's do 1172.85 minus 1073.9 divided by 1172.85 times 100. And once you plug that, you get about 8% difference. So they're not exactly the same, but they are close. So if you decide to do it one way or the other, I will count it as correct. So you don't have to worry about that. You know that for me, the most value when you do a problem is in the development of your solution and not that much on the final value. In other words, to me, out of 10 points, the development is worth 8-9 points, final value just 1 or 2 points. So that will be it for this long video. Thank you for your attention.